Hi, and thank you for this opportunity to present our recent research. My name is Dr. Arum from the Department of Radiology at Eunpyeong St. Mary's Hospital, the Catholic University of Korea. It's my pleasure to share our study titled Association of Hypoxic-Ischemic Injury of the Brain with MRI-Derived Glymphatic Function Parameters in Neonates. To begin, hypoxic-ischemic injury, or HII, is a leading cause of neonatal brain injury. It affects approximately 3 out of every 1,000 live births. Roughly 25% of affected infants go on to develop long-term neurological conditions, such as cognitive delays, behavior issues, and motor impairments. Given this, we know that early detection and timely intervention can significantly improve outcomes. As a result, researchers can increasingly focus on developing reliable and early imaging biomarkers to support clinical decision-making. Now, turning to the glymphatic system. This is a brain-wide clearance mechanism responsible for removing metabolic waste through perivascular space, or PVS. This function is particularly critical in neonates, given their rapid brain development and elevated metabolic demand. In our study, we evaluated two MRI-derived markers of glymphatic function. One is BG-PVS volume, the other is DTI-ALPS index. Together, these measures provide a unique perspective on glymphatic activity in the setting of neonatal brain injury. With that background, our study aimed to assess whether hypoxic ischemic injury is associated with glymphatic dysfunction in neonates, specifically using basic Van PVS measurement and the DTI-ALPS index. We performed a retrospective and single-center study. Among 254 neonates admitted to our NICU between July 2020 and July 22, 127 met our inclusion criteria. Of these, 30 had MRI visible HII and 97 served as controls. All imaging was performed at term equivalent age using a 3T Jimin scanner with a 64-channel coil without sedation. Next, let's review the imaging protocol. We acquired the following MRI sequences: high-resolution 3D T1 weighted and T2 weighted scans, 30 direction diffusion tensor imaging, and suspectively weighted imaging. Moving on to imaging analysis. For BG-PVS quantification, we used infant-free sulfur for brain segmentation, applied French filtering for vessel enhancement, and performed expert manual refinement. For the DTI-ALPS analysis, we placed three small regions of interest in the projection, association, and subcortical white matter fiber tracts. The ALPS index was then calculated as a ratio of the water diffusivity along breadths across the PVS. For our primary analysis, we employed multivariable logistic regression to examine the association between glymphatic parameters and HII. Importantly, our models were adjusted for key potential confounders: sex, gestational age, corrected gestational age, birth weight, and mode of delivery. Now let's turn to the results. This table summarizes the demographic and clinical characteristics of both groups. There were no significant differences between the two groups except for mode of delivery. This brings us to our first major finding. Neonates with HII had significantly smaller BG-PVS volume and BG-PVS fractions compared to the control group. Interestingly, the DTI-ALPS index did not show a significant difference between the two groups. These representative images clearly illustrate this difference. On the top, We see a neonate with HII who has a BG-PVS volume of 25 cubic millimeters. On the bottom, in a neonate without HII, the PVS volume is visibly larger at 30-90 cubic millimeters. Next, we look at developmental changes across CGA. We found that BG-PVS parameters decreased with increasing CGA, while the DTI output index increased. Notably, this trend was observed only in the control group, suggesting a disruption of normal glymphatic maturation in neonates with HII. Additionally, we assessed the relationship between structure and functional markers. We found no significant correlation between BG-PVS measurement and the DTI output index. This implies that the two metrics may reflect different and complementary aspects of glymphatic function. Further, we performed multivariable regression to assess independent associations. Both smaller BG-PVS volume and fraction were significantly associated with HII even after adjusting for covariate. In contrast, the DTI output index remained not significantly associated. So, what do these results suggest? Our findings indicate that glymphatic dysfunction, as reflected by reduced PVS volume, may play a key role in the pathophysiology of HII. This may be due to factors like astrocyte swelling or aquaporin 4 dysregulation, which can narrow PVS. Also, the age-related trends we observed in healthy neonates, PVS narrowing and output index increase, are opposite to parents reported in older populations, emphasizing developmental differences. Our study has limitations. It was retrospective in nature and focused on specific brain regions. Looking forward, longitudinal studies are essential to evaluate how glymphatic functions evolves and whether it can predict neurodevelopmental outcomes. Moreover, future work should include whole brain glymphatic mapping and white matter PVS analysis. To conclude, neonates with HII exhibit altered glymphatic function, especially in the BG-PVS. These MRI-derived parameters show potential as early imaging biomarkers for identifying at-risk neonates. Thank you for your attention.